Hi, everybody. I want to thank you for your patience with me. In the last week, I know I've been absent a lot. I'm hoping it won't be too much. It won't be a lot coming up in the future. So just bear with me, folks. Thank you. Anyway, yesterday you did a lab about what we call Ohm's law. And Ohm's law really relates the two quantities that we graphed, current and voltage. And Ohm's law, says that there's a certain relationship between these two quantities, well, for things that are what we call ohmic. Right? Something that's ohmic behaves according to Ohm's law. So Ohm's law, I'm going to say for circuit elements that are what we call ohmic, says that current and voltage are directly related. Okay? And so you should have seen that one of your sets of data showed a nice straight line like that. This is an ohmic device, an ohmic circuit element, or an ohmic device. All right, here's a different, also ohmic device. Here's yet another one. All right, those all show a direct relationship or between current and voltage. And well, how do we know, or what's the difference between each of these? Well, the difference is, if we look, say, at, I don't know, to get this much current in any of these devices, well, you'd need, this much voltage for that one. You'd need this much voltage for the red one. You'd need that much voltage for the green one. So you need different amounts of voltage to get the same amount of current in different devices, even though they're all what we call ohmic. All right, so there's some other factor that affects this. The green one, we need a lot of voltage to get a certain current. The blue one, we need a very small amount of voltage to get that same certain current. All right, and so we say that current and voltage are related by another quantity that we've called resistance. All right, so Ohm's law, really, there's a lot of ways to do it, but, well, there's three ways. But that is the way we see it most often. All right, where V, as you know, is voltage, measured in volts. I is current, measured in amps. And R is resistance, measured in ohms. Ohms, that's an omega. All right, we all know that already, I think. Now, the other things we should talk about here, well, like what's the difference in these three lines, the green, the red, and the blue? What's the difference? Well, like we said, for the green one, we need a pretty big voltage to get a certain current. For the red, we need not so much. For the green, we need even less. So that says that these three lines have different resistances. Right? If you need lots of voltage to get a certain current, that means that that device has a big resistance. If you only need a tiny little amount of voltage or energy per charge to get a certain current, that means that a device has a small resistance. All right? And the big deal that hopefully we can sort of see from this is if we're careful to plot voltage on a y-axis and current on an x-axis, this looks a lot like y equals, well, I guess, x times m. You know that formula for a straight line, y equals mx plus b? But if the y-intercept is 0, then that b is just 0. So that says that, normally you see a y equals mx, right? But that says, yeah, voltage is on the y, current's on the x, and that says that resistance is the slope. All right, so for a big deal graph, slope is resistance. You just have to make sure that voltage is on the y-axis and current is on the x-axis. Sometimes they'll reverse those on you. Sneaky people. Okay? Now you saw, I hope, that there was in the lab you did, there was something like this. All right? And this is what we call a non-ohmic device. Your light bulb was non-ohmic. All right? So non-ohmic, if you notice, the slope of that thing keeps changing. So non-ohmic things have non-constant resistances. Ohmic devices have constant resistances. That's the big difference. Okay, almost everything, everything we deal with in problem solving will be of that variety, ohmic, all right, where resistance always stays the same. Okay? Okay. Well, let's see, what else about this? That's a good start. Yeah, well, I guess it's time to talk about, a bunch of you. I tried to pick 3 different resistances in the lab. I picked some 5-ohm resistors, some 10-ohm resistors, and some 25-ohm resistors. So every one of your groups should come up with a resistance from your graph, again, by finding the slope. That's what I was asking you to do. That's pretty darn close to one of those values. All right? If you didn't come out pretty darn close to that, then you should check your work. All right? Because that data typically comes out really well. And I already heard a bunch of yesterday saying, wow, we got 0% error. That's awesome. All right? There's something about a tolerance that I mentioned in the lab. Forget about that. All right? Because some of them say on them plus or minus 5% or something like that. So it really could be like, 5% of 10 is 0.5. So they really might be like 10.5 ohms, but yours didn't have the tolerances written on them, I think, so forget about that part in the lab. Fair enough? All right. So we talked about slope, very good. We talked about the Ohm's law, very good. Yeah, okay. So we have these 3 different, right? Big resistance, middle resistance, small resistance. The next, hopefully, logical question is, well, why do things have different resistances? Why do resistors have different resistances? Well, I'm going to adjust this question, right? And I'm going to talk about that when we get back. The resistors that you used yesterday, we can really just get rid of that and say, why do wires have different resistances? Because literally, if you smash one of those resistors open, you take a bowling ball and you smash it. It's just covered in some ceramic stuff. But inside, there's just a whole bunch of wire. All right? So the question is, apparently different wires have different resistances. Okay? Well, why is that? Well, it's kind of like for this reason, because current-carrying wires are a lot like water-carrying pipes. So what kind of pipe would allow water to flow really easily? You can even think about this. What kind of straw can you use that allows you to drink a lot of soda really fast? McDonald's has like straws that you can just totally chug soda with. All right, and what's true about those straws? Well, for one thing, what kind of pipe or what kind of straw allows you to drink soda or flow water really easily? They're thick ones. Or fat ones. All right, next actually, I'm just going to jump over here and kind of, we'll sort of use this as an analogy to think about this. So what kind of wires allow electrical current to flow really easily? Thick ones. Or fat ones. Or ones with what we call really large cross-sectional area. Now this is maybe harder to get, but I bet it'll work with you. If you had to drink out of like a 10-foot long straw or like a 6-inch long straw, the 6-inch one is going to be easier to drink your soda out of. So that means that shorter pipes allow water or any fluid to flow more easily. And that literally means that shorter wires allow current to flow more easily. Or we say with small length. Now, here's where the analogy sort of breaks apart, so we can sort of forget about this now, but let's, so that's true. Those things are both true. Well, let's focus more on this now, right? And if we say, well, there's something else about different wires that can make them that can allow current to flow more or less easily, and that has something to do with, 3, what the wire is made of. So like a lot of wires in your house are almost exclusively made of copper. If you have an old house, then some of the wiring might be aluminum. But copper is the predominant one that people use now. And so, wire is a good conductor. Copper is a good conductor. Gold is an even better conductor, I think. Aluminum I don't think is as good a conductor, but that's a property of the metal, and we call that, this has to do with something called resistivity. Not resistance, resistivity. All right, this is what we call a property of the metal itself. And a fourth one is actually temperature. So there's this thing called the Large Hadron Collider. It's a big underground tunnel, about 16 miles in circumference, I think, underneath France and Switzerland, and they fire beams of protons and other beams of protons and smash them together, and it's where they found that thing called the Higgs boson in July of last summer. I don't know if anyone's heard of this, but in order to do that, you need to, there's some superconducting magnets in there. Long story, but there are these superconducting magnets. So how do you make superconductors? You have to make things really cold, all right? So here, this definitely is falling apart. There's nothing about a cold pipe that's going to make water flow more easily. But a cold wire makes current flow more easily. Or we say that if we want, a good current to flow easily, we need a low temperature. All right, so here are 4 things that affect the current carrying capability of a wire. Okay? Now this one we usually just keep constant. All right, at least in the problems that we solve, we'll keep it constant. But you should know that the colder a wire is, the better conductor it is. Okay? Now, let's talk about actual relationships. We want to talk about how resistance, or how we calculate the resistance of a conductor. All right? So resistance, there's an equation for resistance. This says, for current to flow easily, that means small resistance, right? So small resistance equals big cross-sectional area. That's called an inverse relationship, right? So resistance must be inversely proportional to cross-sectional area. So cross-sectional area, we call that A. It's measured in square meters. To flow easily, we want a short wire, small length. So that means that small resistance is small length. That's called a direct relationship. Whoops, direct relationship. So length, we use as L. We measure it in meters. That's going to go up here, a direct relationship. The bigger length is, the more resistance there is. And then there's this resistivity thing. This is tougher. All right, resistivity, we use that, rho. It's like a lowercase p, but in Greek, rho. All right? So rho is the variable we use for resistivity. Its units are ohm meters. Ohms times meters. I'll show you why that is. And for small resistance, we want small resistivity. Another direct relationship, which says that rho goes up here also. So there's an equation we can use to find the resistance of any conductor, any wire. If we know what it's made of, translate that into its resistivity. If we know how long it is, and if we know what its cross-sectional area is, we can calculate its resistance. The biggest hiccup here people will run into is getting this word confused with this word. Resistance, resistivity, two different things. Luckily, if you grab your reference table, which you should anyway, grab your reference table, I'll wait, go. You're opening your folder, you're pulling up your reference table, yes you really are. Okay, so you have your reference table, and if you look in the, we gotta look in the electricity section. Actually, I gotta pull out my reference table. Uh-oh, I was singing and not, I don't even have one. So when you open up your reference table to the electricity section, first of all, you'll see that on the right side there's a whole list of variables and what they, what symbol means what. So that's a nice reference. And you'll also notice there's a table of resistivity values. I really gotta find mine. Hang on. So, yeah. Go down to the, electricity part, right? So here's where it tells you what's what. Yeah, capital R is resistance, rho is resistivity, and here are these resistivities. Remember how I said we'll always just keep temperature constant? They're saying, okay, 20 degrees Celsius. That's like a good room temperature, right? So here are the resistivity values for a few common conductors, right? Like I said, we use copper a lot in household wiring. We used to use aluminum. Gold they use in some fancier stuff. I don't really know about nichrome. I've heard of silver. I don't know when they use it in conductors. Tungsten, I think you might have heard. That's typically what the filaments in light bulbs are made of. Okay, so there's a few common conductors. All right. What I don't have, unfortunately, is a example problem for you to work through. Hang on. Well, what I'm going to do is just sort of talk you through an example. I'll even write it down here. Let's say, I'll just sort of draw it. Let's say that we have a wire. It looks like this. And let's say that the radius of the wire is, I don't know, 1 millimeter, and that it's 2 meters long, and it's made of copper. And we want to know what its resistance is. Well, we're going to say that the resistance is what we call rho L over A. All right, well, rho for copper, if you look through your reference table, oops, rho for copper. Come on, where are you, rho for copper? Oops, that's not it. Rho for copper. 1.72 times 10 to the negative 8. Come on. There you go. 1.72 times 10 to the negative 8 ohm meters. That's rho, resistivity of copper. Length is 2 meters. Area, well, this is the area. This is a cylindrical wire. How do you find the area of that circle? If you know the radius, we do pi r squared. If you can't remember that, that's actually in the reference table too. People will say 2 pi r, that's circumference. All right, so we can say that the resistance here, you could actually calculate this right now if you want, or just do this, put it all together, and we get 1.72 times 10 to the negative 8 ohm meters times 2 meters over pi times, careful here, 0.001 meters, because we need our radii in meters. Don't forget to square. So that resistance, whoops, that resistance, grab my calculator. Let's see, 1.72 b negative 8 times 2 divided by parentheses 0.001 squared times pi. Where's the pi button? There it is. Equals, we get a resistance of 0.011-ish ohms. So, you know, that's not nothing, right? You were working with resistances of like 5, 10, and 25 ohms. This has 1/100 of an ohm, which is small, but it's not 0, right? And this is, you know, that's a pretty skinny wire with that's not that skinny, I guess. That's probably a pretty normal wire, all right? 6 feet long or so, normal size wire, has that resistance, has some resistance, okay? In most problems that we solve that have to do with actual circuits, we'll forget about the resistances of wires. We'll just talk about the resistances of resistors. But if there's a question that talks about the resistance of a wire itself, that is how you do it. Okay? There are a few problems in the sheet that you'll get in a couple minutes that deal with this relationship. There are also a few plain old Ohm's law ones, and there's even one about current that will go back to a different relationship you learned earlier. Okay? So thanks for, like I said, folks, thanks for your patience, and I'll see you on Monday. All right, finish the problems that you get now. I mean, you have another 20 minutes, so you might finish them before you leave. If you don't, finish them for Monday. Okay, folks, happy weekend. Adios.